And thanks a lot for the invitation. So it's my third week here, and I really enjoyed every minute here. So it's such a great place to be. Good. So in my talk, I want to take this dynamical response from the linear regime to the nonlinear regime, which is in the title of our conference. But it will not be about quantum magnets, but will actually focus on the classical magnets, as most of these non-equilibrium effects can actually be understood from a purely classical perspective. So I'll start with showing you a number of movies and slides which give you a feeling about one idea, namely how we can pump Goldstone modes to get non-equilibrium states. And maybe some of those who have been here 2 weeks ago, they have seen some of the pictures before. But the main part of the talk will be the last point. Namely, we would like to look at a Trilton ferromagnet, and I want to convince you that there's a good reason to label some state like that as an active magnet. So what is an active magnet? That's steered from a very important field of theoretical physics or experimental physics also, namely the field of active matter. So that's a story about looking at active agents, so flocking birds, beehives, microswimmers, whatever you like. So, for example, if there would be a panic in the room and everybody would flee out of the room and go through the door, that would be a typical active matter scenario. So if you like, we have a system which doesn't have any detailed balance, even on the microscopic level, and there are some emergent collective behavior which comes out. That's the very loose definition. Yeah, and if you like, the guiding question is, can we make our beloved magnets somehow active? Can we go in this regime using ordinary magnets, and what can we expect? Well, first question is what could happen in principle, and yeah, you can just look at some of the typical active matter system, like here some bacteria swimming around, and now just imagine this would not be bacteria, but it would be vortices, fermions, domain walls. Yeah, obviously very different from this type of states we are usually looking at. Now, another thing which can happen is out of equilibrium we can start to pump currents. Yeah, so like a solar cell pumps electric currents, which is a very non-local thing that could be an effect. We can think about new phases of matter, so stuff where things are moving, time crystals, pattern formation. Certainly there will be phase transitions with new universality classes, and we can copy obviously a lot here from the active matter literature. And we should realize that all the rules of the game we are used to can change when we in this non-equilibrium situation. So when we think about Kibble-Zurich, Mermin-Wagner, Goldstone, you name it, we have all to rethink these concepts when we go in this out of equilibrium situation. Yeah, can think about building some small machines, and ultimately it's just a nice playground for us to play with, I think. Good. So active magnets is our goal. How can we create them? And the first thing one has to realize that solid and non-equilibrium is not a good pair of things, because most solid state systems rapidly relax towards equilibrium. Take a piece of copper and try to displace with an electric field the Fermi surface by 1%, and you'll see your copper will melt. That's just not easy to get a solid state far out of equilibrium. So natural target are the soft modes of a system, so which are all types of quasi-Goldstone modes which we have. So this could be rotation of magnetism, sliding of an incommensurate texture, but also when you take a single fermion or a domain wall, moving them you can also view as one of these soft Goldstone-like modes, because it doesn't cost an energy to displace a magnetic fermion, for example. Good, so that's our guiding principle. We want to take these Goldstone-like modes and we want to activate them by pumping. How does this go? That goes very simple. Namely, let's apply just, let's say, an oscillating field to a magnet. Then we know when you do linear response theory, then we get oscillations again with the same frequency omega. And when you go to quadratic order, then things happen at 2 omega and at 0 frequency. Yeah, and now we are, if you like, lucky, namely at 0 frequency is precisely where all the Goldstone modes lie. Yeah? So if symmetry allows, it's kind of unavoidable that we activate, do something to the Goldstone modes just in second order perturbation theory, yeah? not worse than that. And the typical consequence, and I show you 3 or 4 examples for that, is that the angle describing the Goldstone modes will typically grow linearly in time. So let's do an example. Let's start with the helical state of just a helix in a chiral magnet. And we drive it by an oscillating field in x direction. And that's, if you like, a little bit schematic outcome of a simulation we show. So you get these small oscillations on the frequency of the drive. So these are these little circles. But on top, you see you get a net rotation of the helix. So the Goldstone mode of this thing is a helix, or equivalently is a overall rotation, or equivalently a translation of the helix. Yeah? So which means you really realize something like an Archimedean screw, and we have shown that you can use this to transport charge, heat, spin, stuff like that. Yeah? And it's also, as it's an effect of second order perturbation theory, it's actually relatively straightforward to calculate that, and that's shown here. So the blue dots are simulations using standard micromagnetic simulations, and one can actually calculate this. So this is the screwing frequency as function of the driving frequency. You drive the system by gigahertz, and this rotates by megahertz, and you can easily calculate this, or relatively easily calculate this analytically. And you get sizable effects. Next example is, let's take a magnetic skyrmion, so an obvious target, because we know they move very little pinning, they move easily around, and we put that in oscillating fields. So more precisely, we take an oscillating field here in z direction, and we break the rotation symmetry by having also a small in-plane magnetic field. Yeah? And here the relevant Goldstone mode are translations. Yeah? And not surprisingly, the skyrmion moves here, and actually this is in a regime where the physics is very similar to this caterpillar. So the mode is about changing the size. It's the breathing mode which changes the size of the skyrmion, and it uses some friction to make a net motion. And let me again say that's not a much more challenging calculation, but also here you can compute this analytically. So the blue dots are actually simulations. The blue line is the corresponding theory, and when you look at the theory, you see there's some very different regimes. When you excite this resonantly with this breathing mode, then it's this friction-assisted motion of the caterpillar. While when you excite it at high frequencies, then you just get magnon emission, which is not uniform in space, so you get a rocket-style propulsion by magnon emission. Yeah? So, but main message is, doesn't matter. If symmetry allows, this thing will move if there's no pinning. Yeah? So that's the main message here. Good. Now these were all simulations and theory, so I should show at least one experimental examples here from the Carbone group in Lausanne. And they looked at the skyrmion lattice, and what they did to the skyrmion, so here's a picture of the experiment, and what they did to the skyrmion lattice is shooting with a laser on it. Yeah, so you do an ultra short laser pulse, and what you observe is that after the pulse, the skyrmion lattice has rotated by a few degrees. Yeah, so here's, for example, the knob, and then you apply a second pulse, and it again rotates by a few degrees. Yeah? So each pulse induces a rotation by a certain angle. That's the rotation degree as function of the flux of the laser. And obviously there's a threshold because there's spinning by disorder, so you need a critical strength for this to happen. But then these guys rotate from the pulse. And the physics is very similar to what I have shown you before. So let me just say what the physics here is. So what you do is actually the laser pulse is circularly polarized. So it creates effectively a magnetic field pulse via inverse Faraday effect strength which we know. And then this field pulse excites the same mode which are used for this motion of the skyrmion, namely the breathing mode, where the size of these skyrmions oscillate. And then these oscillations then trigger this rotation. And this is, there's also an experimental proof for this picture. And the experimental proof goes like that. You now take two pulses, but the first pulse is too weak to get this thing moving. Yeah? So it's below the pinning threshold. So one pulse is doing nothing. But then if the second pulse, but the first pulse still excites this breathing mode. Yeah? And if then the second pulse is in resonance with that, then the motion starts. Yeah? So, and this is precisely shown here in the experiment. The frequency matches precisely this breathing mode. There's no question that this is triggered by this breathing mode inducing the rotations. Good. Let me skip something here. Yeah. Now there are many more examples of that. So for example, there are many experiments on nano oscillators in ferromagnets or antiferromagnets. So you have a magnet, pass a current through it in various geometries, and then the magnet starts to oscillate. So as you typically need large currents, you do this in nano systems. But also the AC Josephson effect, you can think philosophically as something being very similar to this activation of a Goldstone mode and by a wide non-equilibrium situation. And I'm sure there are many more examples on this list. Okay, so what have I told up to now is we have some system with some quasi-Goldstone mode, and it's very natural to activate them when you do a second order response. There are some forces going to it, and then things start to rotate, move. Yeah? But I promised something else in my first slide. I said something about active matter. No, sorry, that was the sentence for the next slide. So here, I just want to remind you what are the relevant modes in the magnet. It's spin rotations, obviously, translations, rotations, and especially also interesting is thinking about defects in the system, domain wall vortices, and so on, and getting them moving. So now comes the sentence. So is this already active matter? Yeah? So you want to get to something like that, but I've shown you only some boring uniform motion and rotation and nothing like we have it here. So what could we do to make this now a truly collective effect? After running a movie, I have always to click once on my slide here. So we obviously need more structure. Now, one way to do that is actually now saying, oh, let's build a machine, let's say, out of magnetic nano oscillators. And that's done here. That's an example from the work of a group in France who tried to build neural networks out of these nano oscillators. So that's obviously what we can do, but yeah, so we want to do something simpler. That's too complicated for me. Let's do something very simple. And yeah, here's what we want to do. So what we want to look is an XY ferromagnet driven out of equilibrium. So here is the Hamiltonian. So we start with the dominant term, which is an XY antiferromagnet. Then we lower the temperature and look at a system which then develops an out-of-plane component at some low temperature. And you can describe this by some anisotropy terms if you like, but it's not so important what the physics is. So we want to look at a system which first orders antiferromagnetically, and then at lower temperature, it develops an out-of-plane component, so it becomes a ferrimagnet. Now we apply an oscillating field. The fact that it's an oscillating field is not important. The claim is anything driving this out of equilibrium should have the same effect. Yeah? Whether you excite with a laser some electronic modes, and then there's phonons raining down and whatever, but this is just convenient for calculations. Good, and if you like, what we want to do when I show you simulations, these are simulations of Landau-Lifshitz-Gilbert equations, so simulation of the classical dynamics, and we have to think about frictional noise in this context. Good. Okay, so let's look at the system. So as I said, in equilibrium, we want to look at a system, whereas when I lower the temperature, I have a phase transition from an equilibrium XY magnet to an equilibrium ferromagnet. Yeah? And now we apply an oscillating magnetic field and ask, what does change? Well, first for the XY magnet, so I said typically you activate the Goldstone mode, which would be a rotation of the magnetization, but by symmetry, this thing doesn't know whether it should rotate clockwise or counterclockwise. So, which means that this state will first not show any net rotation, so because it doesn't know in which rotation to go. But that's different in the ferromagnetic state, because now the ferromagnetic component of the ferromagnet gives us a sense of rotation. So, which means when I drive the system and there's no pinning by disorder and so on, then it's clear that this guy will rotate, and the let's say the up ferry component will rotate clockwise, the down ferry component will rotate counterclockwise or opposite way. And so the rotation direction is determined by the Z polarization of the ferromagnet. Good. So let me just show you that we understand that again. So here is, if you like, a mean field calculation, which means you switch off noise and let a simulation run. That's very simple. And then you can calculate the rotation speed, and the rotation speed is proportional to the square of the amplitude of the driving field, as I said before. And then you can again calculate this analytically. Here we put only the effort to do this close to the phase transition. And there you see that the rotation speed actually grows linearly with the order parameter of the ferromagnet, so it's linear to the magnetization. We'll need that later. Good. So again, I showed you rotation, but we have not yet seen that this is an interesting active magnet system. Yeah? So where's now this thing getting active? For that, it's worthwhile to now think about the fate of a domain wall. Yeah? So we have now a domain wall of the ferromagnet. And we said, we have now to consider a domain where on one side the spins rotate in one direction and the other side they rotate in the other direction. And you remember the dominant order parameter was XY order, and now the XY order is in deep trouble, because sometimes during the rotation these domains look just in the opposite direction, which costs a lot of energy. So this guy is extremely unhappy. So we have to the system has to find a solution to that, what happens here to the domain wall. And without noise and so on, you can easily, without noise and for a 1D domain wall, you can easily calculate this analytically. There should be a movie for that. Namely, a static domain wall is not possible, and instead you find that the domain walls move spontaneously. And whether they move right or left is now not decided by, that's decided now by spontaneous symmetry breaking. Yeah? So there's still a rotation symmetry. So, and they move with really a fixed finite velocity, so all move with the same speed. Good, so that's, now it gets interesting. Namely, we see that these domain walls become active and move spontaneously. Good. Now let me try to show you we first show you a little bit of pictures, but then we do a serious field theory of that. So here's let's look at a picture. So what we want to do is a quench from an XY magnet into the ferromagnetic phase. And first I show you the equilibrium situation. Yeah. Next movie is equilibrium. So does it start? Yes. So this is what you maybe have done yourself in your computational physics course. You cool down and then you quench in some domains and domain walls, and that's what we're used to. Yeah? And now we have to think, this picture has to change when now these guys become mobile objects. So we can do the same simulation in effective model for this thing. So now this is with drive, so with this rotating domain walls and moving domain walls, rotating spins and rotating domain walls. and what you should see is that now all the domains are wiped out. So they move and annihilate each other, find each other now much more easily, and they are just gone. On a time scale which is proportional to this 1 over the velocity and the initial distance of these defects. Okay, so that I think shows dramatically that we now have some active matter situation which really depends differently. So the quench dynamics is completely different, and now we get more ambitious and want to look at the phase transition in such a setting. Good. And importantly now, the most important layer comes into game, which I suppressed up to now, which is noise. So, and I should say the credit for what I'm telling now goes to Cologne, Romain, mainly, from Sebastian Diel's group. Good. So let's write down a theory for what we are seeing. So it's clear we want to have a theory of the XY magnet here, written by this angle theta. And then we have a standard Ginzburg-Landau theory of the Z component of the magnetization. And they couple in a natural way by time derivatives. But now comes the one new thing, namely that the induced rotation is proportional to the magnetization that I've shown you before. So the rotation of the angle of the XY magnet is proportional to the magnetization of the system. And that changes everything. So that's now the game changer, which makes this a true non-equilibrium problem. And so let's, so this system of two-coupled equation is still a bit confusing, but it turns out one can reduce it to single equation just for this variable theta. And now we have to recover what's in there. Now the control parameter, so delta is proportional to the control parameter of the ferro transition. That now controls damping. And in the ferromagnetic phase, this damping term becomes negative, which allows for net rotation, because then this negative damping term will balance with another nonlinear damping term, which comes from the nonlinearities of this Ising field theory. And they will find this new state with a finite rotation speed. So we have here this, the phase transition is described by this damping becoming negative. Another interesting feature, so I said we have these domain walls moving with the finite velocity. So indeed for the critical theory, this velocity term is very important. Good, and here comes the main hero, which is noise, that we have to take now seriously at the phase transition. Okay, the thing is a critical exceptional point, so I have to explain what that means. So critical exceptional points is something every of you knows, namely from your 101 physics course on harmonic oscillator. There's a special point just between the overdamped motion at large friction and the underdamped motion at weak motion, where you just have this, where just critically damped, just sit between overdamped and underdamped. Now what has this to do with the field theory? So when we are in the XY phase, and so here the dashed line is the imaginary part, solid line is the real part of the excitations. In the XY phase, we have an exceptional point at finite momentum. And when we go to this point of zero damping, then this exceptional point moves and merges here with the k=0 point where the phase transition happens. So philosophically, this is a theory of a critical exceptional point. So what happens at such a point? Let's go back to equilibrium. So equilibrium is a story about fluctuation dissipation theorem, and fluctuation dissipation theorem tells us noise induces fluctuations, friction stops fluctuations, and they are in balance by detailed balance theorem, and make sure that everything just fluctuates according to the laws of thermodynamics. Now this rule is broken, and I showed you that friction vanishes at q=0 at this critical point. And now we are in deep trouble, because the one thing which stops fluctuations, usually, friction, is switched off. So fluctuations will go wild, and if you just look at the Gaussian theory, then you indeed see these fluctuations grow with 1 over q to the 4, because at q equals 0, the friction is missing. Yeah? We fine-tune, at the phase transition towards the ferromagnet, this friction automatically tunes to 0. Good. Now the question is what happens? And there are roughly 3 options. One is these fluctuations could destroy the XY order in sufficiently low dimensions. Option 2 is that maybe this is not true and everything, there are some nonlinear effects which kill that. And option 3 is that there's a fluctuation-induced first-order transition. And here the real work is, so now you have to look at the divergences which you get in these theories. Look, what are the most divergent diagrams? And while physics is very different, the math is very similar to what some of you may know as a Brasowski scenario. So you get highly divergent simulations, but they conspire to give you a fluctuation-induced first-order transition. So if you calculate the effective potential coming from these fluctuations, summing up the most diverging diagrams in the RT sense, you get a first-order phase transition scenario. So let me show you this in the phase diagram. So this was our equilibrium phase diagram. You remember XY magnet, ferromagnet. It was with a second-order phase transition. Now for arbitrary weak driving power, in the absence of disorder, the ferromagnet starts to rotate. The phase transition changes its universality class and becomes a fluctuation-driven first-order transition. Obviously, very weak for very weak driving, but that's its fate. And then there's and if you go for slightly larger driving, then also something else will happen, namely that you simply destroy the XY magnet. Yeah, so yeah, we have the fluctuation-induced first-order transition, and actually the driving power needed to destroy that actually goes to the Gilbert damping squared, so that the damping of the system squared. So it's so if you have a system with little spin relaxation, then this happens for relatively weak driving power also. Good. So that's what I wanted to tell. So I want to show you a story about active magnetic matter. And so what we have in mind, or the basic concept is really the guiding principle for us to think about these systems is to say, let's take the Goldstone mode in the systems and activate them, and then let's see what happens. And I think that at least I still have a steep learning curve in this field, so we have to think what is interesting happening. I showed you, for example, triple Zurich is changing, but there are also other Mermin-Wagner theorems are known to be broken so these are known results from the active matter community that you can change the nature of the Goldstone mode, beat Mermin-Wagner and other things. So I think we can learn some of that. And the question is, what can we translate realistically in solid state systems? Now, what we didn't expect before doing that is that you can really get new types of phase transition and new states, not only in the highly nonlinear regime, but for very weak driving. And so that was the example, this XY ferromagnet that was unstable for arbitrarily weak driving and bringing us into a new Goldstone mode. And in this case, the theory was realizing this critical exceptional point where we argued that the fluctuation catastrophe is kind of very generic and drives the system towards a first order transition. Now, if you think about experiments, then the last point is the most important one, namely this is about disorder in the system. Yeah? And disorder comes into two flavors here. Namely, first, it may stop here, for example, our ferromagnet from rotating. Yeah? So so it's not that infinitesimal driving will rotate this, but there will be a critical driving needed to get this thing rotating. But there's also another danger, namely, if you think about the moving domain walls, they can also be pinned by disorder. Yeah? So we have kind of two disorder thresholds which we have to overcome. So it looks as if it's our worst enemy, But surprisingly, we start to look at situations where we see that actually this order strongly enhances the effects which we are discussing. And for that, I have to go back to this. Yeah, maybe I'll make this one point if I have one more minute. So I go back. You remember I did this Kerman lattice rotations? That was the only experiment that I showed you. So laser pulse, lattice rotates, and that were the experiments which showed what happens and what happens when you take two pulses. Yeah? So you do this pump probe, two-dimensional spectroscopy is it nowadays called, type of experiment. And here's the theory, and you see, and that theory is done for a clean system, and you see everything matches perfectly, taking the fact that this doesn't pin, yeah, because it's clean. So this fits perfectly, but there's a but. Namely, here I plotted theta divided by theta 0. So I have normalized this, normalized the amplitude. And if you look at the amplitude, then you see that the theory underestimates the effect by 6 orders of magnitude. Yeah? That means we have made a 6 order of magnitude mistake in the calculation, and we know what the mistake was. Namely, we simulated a clean system, or it's actually analytic calculation. We calculated it for a clean system, and we know that we know that this motion comes at least from the friction from the. So we needed the friction to get this rotation done, and there's much bigger. There's indeed a force which is many orders of magnitude bigger than the Gilbert damping to do the friction, which is this order. And here the disorder actually enhances this effect by 6 orders of magnitude. So that shows that our disorder is not only our worst enemy, but can also be our friend to create these active matter states. Thank you.
Okay, thanks for a very nice talk. Other questions?
Regarding the third bullet point you have down here, activating Goldstone modes as a useful guiding principle, but what's the guiding principle in when you can activate Goldstone modes in this fashion? I mean, what's the general considerations for being able to do that? You certainly, in order to see like a second order response, you have to break certain symmetries, but what beyond that?
Nothing beyond that.
Nothing. There'll always be.
Yeah, so it's always, so in the absence of disorder, that's always the disclaimer. Yeah? So in a real system, there's always some disorder, and that will pin stuff. Yeah, and if you would, so in a perfectly clean system, it doesn't matter how you drive the system out of equilibrium. Yeah, so let's say I have a single experiment sitting somewhere, and then I drive it somehow out of equilibrium. Doesn't matter how. If it knows in which direction to fly, it will fly. Yeah? So if there's not a rotation symmetry or so forbidding, so let's say you apply a tilted magnetic field, so that there's one direction given, then it will move, independently of how you drive the system out of equilibrium. Obviously, when you want to drive it fast and above the pinning threshold, you'll better excite it resonantly. Yeah, so that's clear. Yeah? But the fact, so at least as a theory statement, arbitrary weak drive is sufficient. And doesn't matter, it has only to break detailed balance, and then it will generically do that stuff. It has to be somehow non-equilibrium. But practically, you want to have it sufficiently big to beat the disorder. So that should be the disclaimer. So this is an important point here.
Okay, so maybe this is a related question or even the same question. So
Hi, yeah, I didn't see you, sorry.
I didn't understand exactly why the disorder should change things by 6 orders of magnitude. I mean, this is...
well, first, we don't have a theory on that. Yeah, so I just said, I know that I did a big mistake, yeah, because when I ask, yeah, so what I have to compare is what are the forces coming from this friction term. So we had this friction Gilbert damping alpha, which is very small in this material. We had put in this equation, and that was the one counterforce against moving something, for example. Or that's the one term, this friction we used to have this breathing skirmion to make a torque. And now I know that the force coming from this order holding this fermion is much bigger, much bigger, several orders of magnitude bigger than the force coming from this friction. And so I know that I made a mistake in my calculation. So I think the visual picture you should say, try to walk on perfect ice. So then you have troubles walking because there's so little friction. And if there's a rough landscape instead, it's much easier to walk. And I'm saying, because this alpha is so ridiculously small in this material which we looked at, having the roughness of the underlying landscape that helped to get things moving.
Yeah, thanks for very interesting talk. So perhaps I just wasn't following, but in case of skyrmion lattice rotation, what determines the direction of rotation?
That's set by if you say the net winding number or the external magnetic field or whatever. So that's no issue. There's no symmetry to be broken here.
Okay, thank you.
Hi, Achim. I have two questions. First is, like in spintronics, as you know, one way how you could move a vortex, not a vortex, a skyrmion, not rotate, but move it, is to apply a current, a spin current precisely.
Yeah.
Like in case there's spin torque. Have you thought about ways of trying to do it in an active manner?
Okay, so I told the story of the ferromagnet of putting in oscillating fields, but actually if I would have instead said I put a transverse current and do spin torques, it would be 100% same equation, same everything. It makes zero difference. Yeah? So I just, and as you may know, these spin transfer torque oscillators are done in dozens and dozens of labs worldwide. Yeah? So it's a standard thing to get a magnet rotating when you apply a current. So it's
correct. But the question, could it do it in an active way, not a driven, but
yeah, as I said, so to get it active, you have to couple these things. Yeah? So you could do indeed so these experiments are not done, that people start to couple these nano oscillators, or you could try to make, so the problem, what is the problem? So when you do these nano oscillators, you need very large current densities to get these things rotating. Yeah? And if you would do this in bulk, 3D bulk or whatever, then it would just melt the crystal, but in a nanostructure, you can have much larger current densities. So that's the reason why this is done in nano. It's also done because they want to have as small antennas as possible and sensors as possible. But another reason is that it's really high current densities. So it's not super straightforward to make this into a uniform translation variant system and get these things rotating. And I think you need the right system with small pinning forces and things like that to get this done.
And the second, could you indulge me? I must have lapse of attention. Could you explain again the critical exceptional point? Like how does it arise in that XY system with Z coupling?
Yeah, so the intuition is you can think about the phase transition. You can just forget about the ferromagnet and say, oh, the phase transition is a phase transition from a phase where I'm rotating to a phase transition where I'm not rotating. Now you have to think, how can I make such a transition? What is the most stupid theory to write that down? So this is derived, but you could just also have guessed the theory. And then the natural thing is that you have a linear time derivative term and a cubic time derivative term, and then you change the sign of the first term. So that's kind of obvious. And now you have just to think that the first term is just ohmic friction. Yeah. So therefore, the phase transition is about tuning ohmic friction to zero. Now, before we did this calculation, we expected that for this to happen, I need a critical strength of driving the system out of equilibrium. So it was known, critical exceptional points were known before. So you would think you need so to tune the effective friction to zero, you would think that you need a critical friction. And the surprise was that's not true. If you do the field theory, because of this special Goldstone mode protection, we can get this for arbitrary weak driving. We need this ferromagnetic transition, equilibrium transition, and arbitrarily weakly drive that, then we go already to this exceptional critical point. That's surprising. So this is what we didn't expect before. doing this calculation. Before we thought critical exception points are something deep in non-equilibrium, but now it's just at our fingertips.
Okay, Susie.
Thanks for the interesting talk. Can you say something about the spin transport at the critical exceptional point?
Sorry, I don't see you. Ah, yeah, no, sorry. It's the sound system doesn't allow me to locate the speaker.
I know the U1.
Yeah, so sorry, you asked about the
spin transport, like out of plane magnetization. I know the U1 symmetry is broken, but do you effectively recover it at the critical point?
So which quantity you want out of plane magnetization?
Yeah.
So the critical point is, well, we said it's a fluctuation-induced first-order transition, so it just jumps. Yeah, so.
And when the damping goes away, do you get some algebraic
Oh, at criticality? Yeah, well, it's a fluctuation-induced first-order transition, so there's nothing critical. So it's first order at the end of the day. If everything is said and done, it's first order. So if you just look at the Gaussian theory, then, okay, so the magnetization is the conjugate variable to dtz. So I was writing you down I said there's a fluctuation catastrophe for the, here for the variable phi. So mc is conjugate to dt phi. So now I could translate this to a power. So the Gaussian theory shows a power law in the magnetization correlations, but as I said, it's fluctuation-induced first order, so everything will be gone if things are calculated.
Thank you.
Yeah, thanks for the talk. I'm just trying to relate what you said to very old things that I vaguely remember from my youth, when there was a lot of interest back in the 90s on driving vortex lattices and driving charge density waves. Mm-hmm. There you have disorder, so you need some threshold of force applied, mm-hmm. Electric field or current or something. But you can ask the question above the threshold. Okay, you have some kind of non-equilibrium state. For example, the charge density wave case is something like this. The phase varies sort of approximately linearly in time. So you can think something is rotating. One of the questions that was asked a lot was, are there really kind of phase coherent oscillations? So if you look at like the power spectra, does it have what kind of spectral peak does it have? Does this thing in your oscillating phase, your rotating phase, is it kind of phase coherent? Is it breaking time translation symmetry in a kind of more modern? Actually, we use that language.
Okay, so there are now two separate questions. What you can ask: what happens in a clean system? What happens in a disordered system?
Indeed.
And yeah, so but first the clean system. Where's my phase diagram? No, the phase diagram was later. So this is just simply a rotating ferromagnet. Yeah, so we said even gets rid of domain walls, and it's just rotating, which means it's a time crystal spontaneously breaking the U1 symmetry of time translations. Yeah. And
fluctuations around that rotating state are very
small. So in 3 dimensions, they are completely controlled and boring, and so 2 dimensions. Yeah, so it's the obvious. Okay, the statement
back
is
in those days.
I think the
KPZ like
terms, very good.
None of that.
So if you look at the rotating phase in 2 dimensions, then you get indeed a KPC nonlinearity. Actually, I was doing this calculation on a blackboard 2 weeks ago, and you get a KPC nonlinearity which is proportional to this driving strength, and that's it's a relevant perturbation in 2D, and it destroys the XY order in the so it destroys Koslitz-Taulis power laws. And you get it's only logarithmically growing, yeah? So it's a marginally relevant perturbation, and that's the strict prediction in 2 dimensions. So it's a system. So this, if you go deep in this ordered phase in 2 dimensions, the long range order is destroyed by a KBC relevant term. I think that's the strict statement.
Okay, so if there's no more urgent question, let's thank Achim again.